Okay, so we continue with bipartite matching. And so we have a graph with a bipartition vertex, bipartition A and B, and we're looking for a good matching, a choice of edges, of independent edges that is as good as possible. And so far we had two criteria for such a matching being good. One was that it should contain as many edges as possible, and we proved a structural result telling us how many edges we can possibly fit into a matching, how many independent edges there are in a bipartite graph, depending on some other structural aspects, like a vertex cover of all the edges. And we also considered the question, or the criterion for being good, that just referred to A and looked how many vertices in A can we match. And we were looking then for a set of edges that covered all the vertices in A. Right, now in real life, as we all know, sometimes for an individual, it just isn't equally good to be matched to just any of the people this person, little a, swiped right, but they might have preferences. So they might prefer this to be their match to that, and this is also still positive, but maybe the least favorite of those three. And other people in A might have their own preferences, and so might the people in B. Right, so we might then look for a matching in this graph that makes the people as happy as possible, in taking into account their personal preferences just individually. And if we have a local situation where, say, these two people are matched and these two people are matched, but this little a and this little b actually prefer each other over their current matches, then that in real life would not be stable. A and b would run away with each other, right? So we call this edge subversive. So that's a subversive edge, right? And the question now is, can we find a matching without subversive edges, a matching that is sort of locally stable? Stable in the sense that maybe not everybody is as happy as they can be, but if somebody else would make them happier than they are, then this somebody else has somebody yet preferred to them, so they wouldn't consider it change. Right? So that such a matching where no subversive edges are is called a stable matching. Now notice that I'm not requiring both ends of a subversive edge to be matched. So this, for example, would be a subversive edge as soon as B preferred this partner over that partner, right? And this little a here has no partner at all, which is fine for this edge to be subversive. And in the extreme case, if we have an additional edge between two unmatched vertices, we also call that subversive, right? So the idea is that we can improve the matching when we have a subversive edge in our newly defined local sense. And just adding another edge should certainly also count as an improvement. Okay, so the question is, does every is there a stable matching in every graph with preference lists? Well, if you don't know the answer, here's where to find the answer. You just go to the Swedish Academy and Google Nobel Prizes. And then you will find that the Nobel Prize, or one of them, for economics in 2012, I think, was awarded to two people. One of them is Gallai-Shapley, who's a mathematician, who was one of two authors, the other was Gale. Gale and Shapley proved this theorem. We'll do that in the last 5 minutes of the first half of this lecture. So if you're ambitious, aim high, don't go for Nobel Prizes. So the other, no, I'm joking, of course. So the other person that shared this Nobel Prize applied this theorem in lots and lots and lots of ways. I've forgotten his name. And you can imagine that this is applicable in all sorts of ways. You want stable assignments that don't disintegrate by themselves just because of local agents making themselves greedily happier than they were supposed to be. Right, so the answer is yes. We can always find that, so let's try and do that naively. Here's algorithm 0. Start with any matching. And as the step, or maybe write it here, as the step, add a subversive edge, any subversive edge, if you can find one. Okay. That doesn't work. That's too naive. Can anyone think of a counterexample just off the top of your heads? Start with any matching, doesn't have to be maximal, just anything. Okay, so take any cycle. Then here's a matching, a starting matching. Now, let's suppose that the preferences of these agents here, the people in there, are such that they always prefer their right-hand, their sort of anti-clockwise neighbor to their clockwise neighbor. So this one here prefers this to that. So in this local preference list, we'd have an inequality like this. So this one also prefers the anti-clockwise neighbor over the clockwise neighbor. And you can see where this leads. I just got that wrong. Yeah, so this one prefers that. So we're going for, oh no, so it depends how you read the preferences. So let's say they always prefer their anti-clockwise neighbor to their clockwise neighbor. So this is not stable because this is a subversive edge, right? Just because this person here prefers that partner over that partner. So that will change to this. But then that will change to this, and so on. It will go round in circles forever. Yeah, that would not be such a good idea. So when I advanced this algorithm the first time I taught this, as I was doing that, I was sort of thinking about it as I spoke, and then thought, well, here we might have stopped this behavior by adding this one first. Right? So algorithm 1, start with any matching. Add any edge if possible. And then repeat the step. So we first look, can we add an edge? Not add a subversive edge which entails deleting another existing edge, but just add one. And we add as many as possible, and when we can't add any further edges, then we look for subversive edges. So I was making this up, and of course I didn't know the answer. So is that a good algorithm? Even algorithm 0 has the advantage that if it ends with a stable matching, right, by definition. Right? It ends only if you can't find a subversive edge, and that I defined as stable. The problem was it didn't have to end at all. So this one here, again, can only end if it's stable, but does it end? Well, I didn't know the answer, so I was asking the audience that in that lecture. And at the end of the lecture, a student came up and said, no, here's a counterexample. So that's now an exercise. I don't think it's on your sheet, but that was a very, very nice sort of thing to happen. That during the course of a lecture, the lecturer proposed some stupid question, which wasn't that stupid at all. At least it wasn't so stupid that he didn't know the answer to it. And then one of the students came up with a solution, and I like the solution. It's not trivial. Very nice. Very, very nice. Okay, so that was Julian Pott, like 10 years ago or something. He went on to do a PhD and did very well. So if you don't go for Nobel Prizes, that's one alternative. Okay, so the answer is no, but I'm not going to show you the example. It's not much more difficult to show than this one, but if you want to have fun with it, don't want to spoil that fun. So here's algorithm 2. Which actually works, and I'm going to prove that to you. So let's start with the empty matching. And the step is to match any unmatched vertex on the left, A and big A, by their favorite subversive edge. If it exists. Right, so we look through all the unmatched little a's, only those. And we look for each of them, do they have any subversive edges incident with them? Right, so if little a is unmatched, what does subversive mean? It means that the other end vertex of that edge prefers this little a to their current partner, if they have one. If they don't have one, then that's also a subversive edge. Okay? And then put that in. So we match A by that subversive edge, and then that entails the newly found partner of little a ditching her current partner. Okay. Now, this time it's the other way around. This algorithm clearly ends. You see why? When you want to prove that an algorithm ends, it's always good to find something, some invariant or whatever, that keeps changing in the same direction, and so that it bounces into some barrier and therefore cannot change forever. You see a parameter that keeps growing? Well, everything is finite. Right? So the graphs are finite.
So then in the end we have just picked every little a and big A. Or so
Yes.
there's no unmatched little a.
Yes, but it might be that a little a that is happy at some point might become unhappy later. So you see, when we add a subversive edge, then the new partner of that little a will ditch her old partner, so that becomes an unmatched vertex that can then look for partners again, or we'd have to look for subversive edges there. Yeah?
But I thought it said instead match and unmatched.
Correct. But a vertex can be matched and then later become unmatched. Because adding a subversive edge also entails the deletion of a current matching edge.
We first put n and then it can happen again, because I thought that maybe we just take the ones that are still unmatched and not the ones that we have already.
Yeah, well, we do that. We repeat that step. So we always look at the current matching that we have, and then look in that matching, is there an unmatched little a? Right, and that set of little a's might change. Did you have an idea? Well, yeah?
Can't we just start with the edge with the highest priority and move downwards in the priority sense?
I don't think I understand that. So here's the simple solution. The elements of B always get happier. They would not agree to the implementation of a subversive edge unless it made them happier. Right? So if you just take the sum, the happiness sum in B, that grows and grows and grows and grows, and it can't get bigger than whatever the sum of all edges. right? So that's an easy proof that this algorithm will actually end. And the question is, does it end in a stable matching? Clearly ends. Yeah, I said why. The people in B get happier and happier. So then it's stable. And here's a nice little trick. We only need that at the end of the day. But we'll prove it by induction for every step on the way. So what's the statement we're going to prove? We're going to prove for every little a in big A, either little a is unmatched or it's not incident with a subversive edge. And at the final matching, that proves that every little a, that there is no subversive edge. And a nice observation that has been made is that, or a sort of double observation, is that this algorithm is not so unlike what used to be the etiquette in the 19th century. That is always the men who propose, right? The ladies have to say yes or no, but the men make their choice and say, yeah, I'll go for her. And then they propose, and then they're accepted or not. And so, despite the fact, so the ladies can only say yes or no. They can never say, no, I'd like him, please. So it's asymmetrical, it's not the same for A and B. And although, as I said earlier, with every step, the elements of B get happier and happier, one can still prove, and that's another exercise, that this algorithm produces, amongst all the stable matchings that there are, the one that makes the ladies the least happy and the men the happiest. So I don't know what society did in the 19th century, but they had some sort of, those people that had the say in those days had some intuition about stable matchings and how to engineer their own happiness. Right, so that's an interesting little aside. Yeah. Let's move on to non-bipartite graphs, arbitrary graphs. All graphs are finite. Right? Let's prove Tutte's one-factor theorem. So this is 2, 2, 1. And I haven't told you what a one-factor is. A k-factor for k, a natural number in a graph, is a spanning subgraph, so every vertex has to appear. That is regular, k-regular. So once more, you have to use all the vertices, you can select some of the edges, and your selection has to give every vertex the same degree k. And for k equals 1, one can ask, when does a graph have a one factor? So when can we select some edges that give every vertex degree exactly 1? So if you like, that's a perfect matching of the entire graph, except I define perfect matchings for bipartite graphs, but it's certainly a matching that matches every vertex in an arbitrary graph. Okay, so here's an obstruction. Consider any set of vertices in the graph. So that splits the graph into some components. And some of them have an odd number of vertices, they're called odd components. Some have an even number of vertices, they're called even components. And if there exists a one factor, then the number q of g minus s, that's the number of odd components, cannot be bigger than the number of vertices in S. Because if you have an odd component and you want a one factor, you can try and match up the vertices inside there, but at least one will be left over. Right? And that one, if it's going to be matched, has to send its edge, or we have to choose a matching edge that goes to S. And we can't use the same vertex for more than one component because they have to be independent. So we can't afford, we can't find a matching if S has fewer vertices than there are odd components of G minus S. So that is clearly necessary for the existence of a one factor. And the theorem says that this is also sufficient. Right, and V is now the vertex set of the entire graph as usual. Right, okay, so that's clearly necessary, and we'll show that it's also sufficient. It's the same kind of good characterization that we had previously for bipartite graphs, for example, in the marriage theorem. It gives you an easy-to-check certificate for the non-existing existence of a matching, of a one factor. Right? It's easy enough for me to persuade you that a one factor exists if I know it. I'll just show you the one factor. It's harder for me to persuade you that no one factor exists. I can show you some attempts, and we can't add another edge. Some vertices are unmatched, yeah, but we can't find two adjacent vertices that are unmatched, but maybe we chose the matching badly, and so on. So that's complicated, and the theorem assures me that if there is no one factor, then such an S exists. And if I know it, then it'll easily persuade you that no one factor exists. So we just count its elements. We look at the components. It's easy to compute the components of a graph. And then we count whether they're odd or even, and then there we are. Right? So that's a good characterization in that sense, that it supplies us with easily checked certificates for one direction of this double implication, where for the other direction there is an obvious natural and easily checked certificate already. Okay. So, proof. We'll have to find a bad S. I'll call it a bad S, an S that doesn't satisfy this, for any G that doesn't have a one factor. Right? So let G be any graph, which way around shall I put it, without a one factor, have to find a bad S. First step, without loss of generality, G is edge maximal without a one factor. So what does that mean? It means that it doesn't have a one factor, but as soon as we add another edge, it will have one. And why is that? Well, log without loss of generality. Well, we have our given graph. We have to prove that if the given graph doesn't have a matching, then we can find a bad S. So let's add edges to this given graph until it's maximal, edge maximal, without a one factor. We can do that. And then let's apply the result, which I'm assuming now we have proved for edge maximal graphs without a one factor. Let's apply that to this graph made edge maximal, call it G prime. Then we'll find an S for the G prime. My contention is that this S works also for G. Why? Well, G prime has some more edges. If this is the S for G prime, if this picture shows G prime, so this S is bad, there are more odd components than S has vertices. Where are the components of G minus this same S? Where are the odd components? Well, we don't know. So G has fewer edges than this G prime, so some of the components may split into many components. But one thing we do know is that an odd component, no matter how it splits into further components, maybe it doesn't split, maybe it stays whole, maybe it does split, but they can't all be even. If the whole thing was odd, then at least one of them will be odd. So this little s leaves at least as many odd components in G as it did in G prime. So this little s is also bad in G. That proves this. Okay. And now comes a technique which is also very useful more generally. We're looking for a particular set S. So we might ask ourselves, well, if the theorem is true, if such an S exists in our edge maximal graph without a one factor, can we say a little more about it? And indeed we can. So, oh wait, I might use this here. No. So if this is the S, and then there are some components, and S is edge maximal without a one factor, and it's a bad set. Then there are more odd components than S has vertices. This fact will not change if we add edges in those components. They will still have the same cardinality. It will also not change if we add edges in S. And nor will it change if we add edges between S and any of the other components. The only thing we mustn't do is add edges between the components. So our edge maximal graph, without a one factor, will have S induce a complete subgraph in G. I'm calling it G now rather than G prime, because we're in the log. So S is complete. the components are complete, and S, the vertices in S are adjacent to everything. All the edges between S and the components, all the possible edges are there. Well, that's pretty unique. So if the theorem is true, and we're in an arbitrary edge maximal graph hunting for a bad S, then this is what it will look like. Okay. So that makes it much easier, a much easier task to find such an S. And we'll do that in a moment. And then we should prove that whenever we find an S in our edge maximal graph without a one factor that is complete, that leaves complete components, and that sends all possible edges to these components, no matter whether it's good or bad, that will suffice to find. Now, why is that? Previously, I said we're hunting for a bad S. Suppose we're finding such an S, but it doesn't leave enough odd components to be bad. Well, no matter. We'll find a matching as follows. Pair up the even components internally. That's possible because they're complete, and since they're even, we can just find any matching. Pair up the odd components completely except for one vertex, which has to remain, and then match that to S. Okay. Now, when we've done that, maybe we haven't exhausted S, but S is complete, so match the other vertices. Well, that seems to give us a matching of the entire graph if it works, but it shouldn't work because our graph doesn't have a matching. So how can this possibly fail? Well, it can fail if S is bad, obviously, but I'm trying to persuade you that even if S isn't bad, this is good enough. So if S is not bad, how can it fail? Well, it can fail if S itself is odd, because then we sort of start matching up here. If S minus the partners of the odd components is odd. If there's then one vertex left over, which is unmatched, which is the only thing that can still go wrong, then the upshot is that G has an odd number of vertices. Right? Because these vertices here are paired with odd components, so in total they cover an even number of vertices. All these matchings cover an even number of vertices. These edges here cover an even number of vertices. So if there's one left over, then G itself is odd. But then the empty set is bad, and we're done. We're done sort of outside this proof. If G is odd, then the empty set, S, has at least one odd component, which is more than its number of vertices. Okay, so it suffices to find in our edge maximal graph without a one factor any set S that leaves this structure. So all S is complete, the vertices in S send edges everywhere, and these components are also complete. How do we find it? Easy, we just write it down. So we define S as the set of vertices adjacent to all other vertices. Right? That's what these do. They're adjacent to each other and to everything. Okay, so that's now a definition. We're hunting for this. We're defining some set S. And I want to prove that this set S has this property. Well, it's certainly internally complete. And it sends all possible edges to the outside world. Right? So all we have to show is that the components are complete too. Okay. Suppose not. Let's look at a component that is not complete. So there's a non-edge AA prime. Right. Take a shortest path. Now, what I'm going to show you now is the result of just mindlessly playing with the situation. We have so much information already that playing around a little bit and see what happens here, what happens there, and so on, will be enough to get us to a proof. So we can't really lay our hands on A and A prime directly. All we know is that there's no edge here. We want a little more. So we want this situation that we have A adjacent to something, B, this is adjacent to something C, and there's an edge missing from A to C. That is a little more specific than just saying there's a non-edge. But that's easy. We just take a shortest path from A to A prime, any shortest path. And then we consider the first two edges on that shortest path. And this path has length at least 2, otherwise it would just be one edge, but that edge doesn't exist. And then we forget about the rest of that path, and we forget about A prime, and all we remember is this little instance of a non-edge. Okay, now little b is in C. That means it's not in S. If it's not in S, what does that mean? It means it has a non-neighbor in G. If it was adjacent to every other vertex, it would be an S. Okay, so there exists a non-neighbor somewhere in V of this little b. Doesn't have to be in this component. Could be here or whatever. Okay, now, since our graph is edge maximal, if we add this edge AC, we'll get a one factor, call it M1, a set of edges that covers all the vertices and is independent. We get a matching of all the vertices in one. Similarly, if we add this edge, we also get a matching M2. We didn't add this. Okay, just add one edge and you get a one factor. That's the assumption. That's what makes it so powerful to have an edge maximal thing, which came entirely for free. Good trick. Right, and now we just doodle around. We'll wander from this vertex D, alternately using edges in M1 and M2, but staying in G. So we're not allowed to use this edge. We're not allowed to use this edge. But all the same, the vertices in G will also have received a color yellow or red. And at every vertex, we know that there is one incident red edge and one incident yellow edge, unless this vertex is one of those three, or B. Right? So this in particular has an incident red edge, not in G, but only in G plus this. Yes, fine, but we're starting with a yellow edge, and it does have a yellow incident edge, because every vertex does. Right? And this incident edge is not this one, so it is an edge of G. Why is it not this one? Because D is neither A nor C, because D is a non-neighbor of B, and A and C are neighbors of B. That's why I needed this little shortcut here rather than A prime. Okay, so there's an edge in G that is yellow. That takes us to another vertex, and that has an incident red edge, unless it's this one. Can it be that one? No, because we don't have a loop there. So we continue in this way, but we can't continue forever. So how can this possibly end? Well, we'll never get back to a vertex that we had before, because we'll be coming in on some colored edge, but every vertex that we had before already has a yellow and a red edge incident with it. So in particular, we can't end here either. We can't end here on a yellow edge because this is yellow. We can't end here on a red edge because this is the red edge in the matching M2, not an edge in G. Okay, so how can this possibly end? Well, there are two ways. It can, let's say, it ends in a vertex V. If this is in M1, so if the last edge is yellow, then the only possible place for V is this little b. If this is in M2, then the last edge leading to V is red. So we can't get out of V on a yellow edge, and the only possible reason why we can't is that V is one of A and C. Remember, we want to get out of V on a G edge, and this isn't in G. So then V is in A, C. It's one of those two. Yeah, but now we do something very simple. In the first case, this path ends in V on a yellow edge. So we have an even cycle alternating between yellow and red, and it uses this one edge that is not in G. Now let's just toggle the colors in that cycle and look at M2. If we look at M2 in the entire graph, it uses one edge that is not in G, and that's this edge, only one. So if along this cycle we toggle yellow and red, this goes out, this goes in, this out, this in, and so on, then suddenly we have a red matching inside G. Well, that shouldn't exist, so we have a contradiction. And similarly, if we end at V on a red edge, then we're either in C or in A. V is either C or A. Suppose it's C, then we complete a cycle by going to B. Then again, we have a red-yellow cycle that starts on a red edge. Then here, the last edge here is red. We're there. Then we're at this edge, which is neither red nor yellow, doesn't matter. Then we again have a cycle, every other edge of which is red. And the unique edge of that cycle that is not in G is this. Again, toggle the red edges, just move them one on in this cycle to get a matching in G that shouldn't exist, right? Of one factor in G. That's the end of that proof. Questions? No? Okay. Then let me wipe the board, do something else. No, I can actually use the third board. Now this is a little theorem 252 about posets, partially ordered sets. That's a theorem of Dilworth, and it says for every finite poset P, how do I want to put it? The smallest number of chains needed to cover P is the same as the largest size of an antichain in P. Right, so what's a chain, what's an antichain? A chain in a partially ordered set is a subset of pairwise comparable vertices. An antichain is a set of pairwise incomparable vertices. Okay, so if we have a poset, yeah, so the usual diagrams are something like this. Yeah, we don't need that edge because, so I draw an edge, so higher means greater, and I draw an edge when we have successors. So this one is less than that is less than that one, and I don't draw the edge from here to there, although that this is also less than that one. Right, so the poset is the transitive closure of this upwards directed graph. And so, yeah, we could try to decompose it into chains. So how many chains might we need? Well, here's one we could use. Here's another. We don't it's nothing to do with edges. We want to cover the elements of the poset, right? Then, I don't know, this one here and that by itself, something like that. So I needed 1, 2, 3, 4. Chains to cover the entire poset. And now the question is, do I find an antichain of size 4? And yes, here's one. Okay, so these are pairwise incomparable. And this is again of the same type as we had it in the in König's theorem. So if we look at the sizes of the antichains, and of the chain covers, then every antichain is at most as big as any chain cover. We need at least one chain for every element of the antichain, because no chain can contain two elements of an antichain. So this inequality is trivial, and the assertion is that they overlap. Right, same as before. Very, very pretty theorem. And we have the certificates as well as before, right? So any maximal antichain certifies the optimality of a chain cover if the chain cover doesn't use more chains than the antichain has elements. And conversely, any chain cover using only as many vertices of an antichain certifies that this antichain is maximal. So we have certificates both ways. Very pretty little theorem. And again, as with König's theorem, it has a structural version, and that is a double existence statement. There exists a chain cover. Let me just call it curly P. So the elements of curly P are chains, and the union of all these chains is the entire poset. And there exists an antichain A such that A consists of one element of every chain. Right, so that clearly follows. If these numbers are the same, then there exists, take any maximum antichain, take any chain cover of smallest possible size, then they have to satisfy this. So you can't have an antichain other than, you can't afford to pick, well, you can't have more vertices in your antichain, elements of your antichain than you have a cover, but you need one from every cover, so from every chain. And so this and conversely, this structural statement obviously implies this, because if you have an instance, if you have such a chain cover, and an antichain that picks exactly one element of every element of the chain cover, then obviously these cardinalities are the same. Okay, so that's very pretty. There are proofs of this that are not so hard, and in the book I prove it from a graph theorem, and I like that theorem, or this way of deducing this very pretty theorem, because the graph theorem is so much uglier than this, and at the same time stronger. So let me show you the graph theorem. That's number 252. Oops, this is, no, 251. Okay, 251. This is the theorem, a theorem of Gallai and Milgram. It's, I think, 1960 or something, so it's later than Dilworth. And it's a theorem about directed graphs. So for every directed finite graph, there is a cover of its vertices by directed paths. So let me just call that a path cover. Of its vertices. And there exists an independent set of vertices so a set U of vertices that there are no edges, directed edges between A and U, between vertices of U either way. Consisting of one element of every of every P in P. So it's very much in this spirit, or so it seems. But in fact, it's not. We'll see why it's not in a moment. Let's just see first why it implies Dilworth's theorem. Well, given a poset, let's come up with a directed graph. What's the directed graph? Well, easy. Right? We just draw an edge from any vertex, any point of the poset. So the vertex set is the elements of the poset, and we draw an edge from any point to any other point that's bigger. A directed edge. Okay. So then we have a directed graph, and then we find a path cover. A path cover is a directed path. A set of directed paths that between them contain all the vertices. A set of directed paths is a set of points in the poset such that this is less than that is less than that is less than that, and so on. So that is clearly by transitivity, that's clearly a chain. So the path cover defines a chain cover in the poset, and an independent set of vertices is clearly an antichain in the poset. Right? So we get this, and therefore we get that. Very, very easy application. And yet, this is not the kind of structural theorem with certificates both ways and with this beautiful little thing here and so on. Why not? because in a directed path, you can have independent vertices along that path. They're going to be comparable, but in the graph itself, if we now look at the Gallai-Milgram theorem by itself, it doesn't say consider any graph that's the comparability graph of a poset. It says take any directed graph. And here lies the reason for the power of that theorem. It's a much, much more general theorem because this is essentially a theorem about very, very specific directed graphs, namely comparability graphs of posets. This is a theorem about all directed graphs. Much, much more general theorem. The assertion is not as pretty as here. And the reason for that is that when you have a directed path, you can have the first vertex independent of the third, that can be independent of the fifth or sixth or whatever, right? So you can have independent sets that are much, much bigger. So these two have a big overlap. So if you take just one directed path, for example, right, it has a large independent set. But you can cover it by one path. Okay. So it's no longer true that all the independent sets have sizes less than the cardinality of any chain, any path cover. It can be the other way around. So this path here, has what are here. Here are the independent sets. So that's sort of 3 here. But we can make do with the path cover of any one path. Okay. So, and for that reason, you don't have certificates, right? So if you have such a pair, a particular path cover and a set of independent vertices, that path cover doesn't certify that this is a largest set of independent vertices, and indeed it needn't be. Right? And the same the other way around. So it's it's pretty enough, but it's not as sweeping and natural as that one. But it's much more powerful. So interesting little aside. Okay, so I don't want to cover the proof because it's a pretty proof. It's a sort of clever induction proof. But I don't have much more to say about it that is not written in the proof. So it doesn't make sense for me to read out the proof to you and walk you through it. You can do that yourselves. It is part of the course. So yeah, I think I'll stop there. So this is the last section in the matching chapter. We skipped a few sections. All right? They're going to be part of graph theory 2. Right, questions? No. Okay, then I'll stop here. Thank you very much.